Okay, I want to do a video on this quiz because many people had a problem with this first one. Actually, only one person got this first one correct. Not totally correct, but mostly correct. Um, and I thought in general I was trying to be generous with points, but um, the key here is recognizing. Let's see, what do we got? We've got a refrigerant 134A entering an adiabatic compressor at 100 kPa and 0 degrees C. And I give you the volumetric flow rate, and I tell you what the pressure is leaving. I tell you the power in, right? The first question I thought would be straightforward, but it wasn't. You have to go to your tables, and you have to recognize. Let's just look at table A12 first, which is a pressure table. If I look at this pressure table, I can see here that refrigerant 134A. Let me just focus this. All right. At 100 kPa, the saturated temperature is 26.37 degrees C, right? So we are at 0 degrees C. We are at a temperature higher than this. So for refrigerant 134A, I know these numbers are small and you think, oh, you know, negative temperature, that's cold, right? But for refrigerant 134A, 0 degrees C at 100 kPa is a superheated vapor. You can see the same thing as if you go to, I think it's more intuitive. I always think it's more intuitive looking at looking up for pressure and seeing the temperature. But you can see the same thing here. If you go to a temperature of 0 degrees, oops, let's see, this table A11. So if I go to a temperature of 0 degrees C, right, I see that my saturated pressure is 293.01. And our pressure is below that. We're at 100 kPa. So that means we're in a superheated vapor state. And in fact, if you go to table A13 and look up your pressure, ooh, wow, it's really reflective here. Let me turn that off for a minute. Oh, that's legible. If you look at your pressure, right, 100 kPa, and you look down at your temperature, you can see these are all superheated data, right? This is telling you everything above minus 26.37 degrees C is superheated, right? So you can see that from this table. So my expectation was that you were going to recognize that at 0 degrees C, you have a specific volume, 0 degrees C and 100 kPa of 0.21630. And coincidentally, the person that got this correct, I believe, is the only one that actually did the extra credit assignment where they went through that packet, the steam table packet. So this is a matter of recognizing, and this is why, you know, I have no problem giving you the same problem just by changing the working fluid. All I have to do is change the working fluid and change the conditions, and it confuses people because you have to know fundamentally what you're reading, right? The numbers are just numbers. You have to understand, what are those numbers telling you, right? Anyway, so this turns out to be superheated. Oh, I got to zoom out a bit more. So we can calculate a mass flow based on the volumetric flow and the specific volume. So that's correct. So I mean, there was a lot of points taken off here. And then the energy balance. So the energy balance, most people didn't write this out. They just jumped right to work in, well, power in is basically mass flow rate times the change in enthalpies, right? And we're given the power in, that's 35 kilowatts, which is also kilojoules per second. I mean, you rearrange this, you basically wind up with the exit enthalpy is just the inlet enthalpy plus the work in divided the mass flow rate. So, and this makes sense too, right? What are we doing? We're putting work in. We're putting energy into this compression we're putting energy into the refrigerant, right? So you would expect its enthalpy to rise. And that's what happens. We see the exit enthalpy is 280 kilojoules per kilogram. So then we come to our exit conditions at 700 kPa. So now this is where I had a tough time with, a lot of people wound up getting points just because if you didn't, for example, one person did something wrong here and got an enthalpy that was actually within the range of enthalpies at 700 kPa for a saturated vapor liquid. So they recognized that for their enthalpy number, so if you got the wrong enthalpy here, I looked to see if you could recognize where that enthalpy was in your tables. And if you did, you got the majority of points. So anyway, 700 kPa, so if you go to your table for 700 kPa, now this is for a saturated refrigerant, right? Meaning it's not superheated. So it could be a mixture. And you can see here 700 kPa, right? The range of enthalpies are, oh, I lost my place, 88.82 and 265.08. Now, the enthalpy I calculated is 280. So I'm definitely above the 265, right? And that's what I see when I look at my numbers. This is a decimal point here. So my exit enthalpy is greater than the vapor enthalpy at 700 kPa. So I'm still in the superheated vapor state. So I need to find my exit temperature using interpolation of the enthalpies from table A13. So what do? I go to table A13 and I go to the 700 kPa page, 700 megapascals. I'm going to turn this light off again because it's reflecting crazily. And I see, all right, my enthalpy was what, 280 something? Okay, so I'm in between these two, 278.59 and 288.54. And that means I'm in between temperatures of 40 and 50 degrees C, assuming I read correctly to the left here. Yes, 40 and 50. So I take that information and I write it down here, right? I'm in between 40 and 50. My exit temperature is somewhere in there. At 40 degrees, my enthalpy is 278.59. At 50 degrees, it's 288.54. This is just setting up the interpolation equation. If you interpolate, you basically wind up with temperature 2 is 42.3 degrees Celsius. So that was question number 1. This was the hardest one, or this is the one that most people had trouble with. Which I guess I'm not that surprised. Reading things out of the tables is not, it takes some practice. And that's why I think, like I said, the person that actually got the correct specific volume is the one that did the extra credit back in module 3 and actually took the time to go through more practice. All right. Number 2 here, ventilation fan of the bathroom. I basically told you this problem was going to be on there, except we did it in class as cooling. This is basically heating, right? So we're given the volumetric flow rate, we're given temperatures of the building, we're given temperatures in the outdoors, and we're given the unit cost of electricity. The first one is just ideal gas law, right? And I think everyone got this. So I'm not going to spend too much time on that, just calculating the mass flow rate from that. The big thing here I was looking for is making sure you realize, oh yeah, liters per second. You have to convert that to cubic meters, making sure you looked up the constant for air correctly, and also making sure your temperature was in Kelvin. And then part B is the amount of energy to warm the makeup air. So I just drew myself a little sketch here, right? You have makeup air coming in at 11 degrees C. You have warm air into the building at 21 degrees C. This is basically a control volume problem. You have heat in mass in and mass out. If you look at the energy balance for an open system, right, there's basically no change in velocity or height, right? No potential or kinetic change, kinetic energy change. You're just left with enthalpy difference. There's no work in or out of the system, right? There's no electric power element in. There's no stir or fan or anything. We're just looking at the heat in. So we've got only Q in. Again, I think most people recognize this is the equation, right? Cp is 1.005 kilojoules per kilogram. Kelvin, that comes from your appendix. A little. And so you can calculate that, right? Recognizing that the heat into the air is 0.482 kilowatts. And then part C was fairly easy. It was just recognizing that, okay, we've got to pay for this heat, right? So the kilowatts times the dollars per kilowatt hour. And then we have to account for, canceling out this. So we canceled out kilowatts. We got to cancel out the hour, 24 hours per day. And I asked you for the cost per month. And that comes out to be $45.15 per month. So overall, I think most people had no trouble with the second one. There were some minor math glitches here and there that people had. And I don't know if that's because you were running out of time or what. Hopefully I've given you enough time for the final that you're not going to be panicking to get things done. Okay, so that's the quiz. And yes, definitely be sure to email me if there's any questions, or stop in. Again, I'll have class. I mean, I won't have official class, but I'll be in class time next Tuesday, because I know, you have that time free. So if you do have any last minute questions, stop in. Thanks for watching.